In this video, we'll talk about Hilbert space representations. We'll start by talking about alternative bases. Then we'll talk about our representations of Hilbert space. And finally, we'll talk about vector and operator representations. So, a vector in 2 or 3 dimensions can be represented differently depending on the coordinate system you choose. For example, let's imagine that we have a vector that exists. We can describe that vector as a length and some angle with respect to a horizontal. That's one way of describing it. But perhaps a more consistent method would be to define a coordinate system and use the components within that Cartesian coordinate system to define the vector. Let's, for example, take this set of Cartesian coordinates where the x is horizontal and the y is vertical, and then we see that the vector A can be represented as a sub x, which is the component of A in the x direction, or the projection of A along the x-axis, times x hat, unit vector in the x direction, plus A sub y, which is the projection of A along y, and the unit vector in the y direction, y hat. A different choice of Cartesian coordinates will give different components, but it's the same vector independent of choice of the axes or the basis. Let's illustrate that by rotating our axes and calling them x prime and y prime. They're still 90 degrees apart, they're still Cartesian, but now you get a different value for ax sub x prime and a sub y prime. But now these are along the x prime hat direction and the y prime hat direction. And so they describe exactly the same vector, but because of the basis set we choose, that is the prime set instead of the unprime set, we have a slightly different representation. Hilbert space can be considered as an abstract vector space, and whose members can be represented using any basis that is valid in that space. Suppose you have the state of a system represented by a vector S of t. So that's a state vector for the system. This vector lies in Hilbert space. We can express it in different basis sets, bases. We can start by looking at the coefficients of expansion in the basis of eigenfunctions of position operator with eigenvalues y. And that's one representation. And we would write that the following way. We write that as psi, capital Psi of y and t is equal to ket y s of t in the ket, rather, in the bra y. In the basis, another way of looking at it is in the basis of eigenfunctions of the momentum operator p with eigenvalues p. And this would be phi of p and t is equal to bra of p ket s of t. Finally, we could also look at this in terms of the basis of eigenfunctions of the Hamiltonian with eigenvalues e sub n. In this case, it would be the coefficients would be c sub n of t, and they're equal to the projection of the s vector along the nth eigenstate. So all very similar. We project the s vector along the eigenvalue y coordinate, then we project the s vector along the eigenvalue p, or we project the s vector along the state with eigenvalue n. And those give you the coefficients that you need to rebuild the vector s of t in that particular basis. What results then is a vector which can be described as an integral of psi of y and t, delta of x minus y, which is the eigenfunction for the position operator, integrated over dy, and that will give you psi of x and t. You can also write that as phi of p and t, which are the coefficients that you get when you project S along the eigenvalue, the eigenstate of eigenvalue P, times the eigenfunction with eigenvalue P integrated over dP. Gives you the same exact function. Finally, we can also build it in terms of the eigenstates of the energy, in which case it would be a sum, because this would be a discrete spectrum, C sub n, and then the eigenfunction of energy E sub n, which includes the time dependence here and the spatial dependence psi sub n of x. All these are identical representations of the identical vector, although they're in different basis sets. The x basis set, the p basis set, and the energy or the Hamiltonian basis set. Formally, vectors are represented with respect to a specific basis by their coefficients, just as we showed before. So let's imagine we have a specific basis E sub n as our kets. These are the vectors that span the space, the basis vectors. Well, then a vector alpha would just be the sum over n, A sub n, ket E sub n. And the vector beta would be sum over n, B sub n times the ket E sub n. And A sub n is just equal, when you close this with an E sub n, you will pick out simply A sub n, where n is a particular value. And this is E sub n, or alpha, the state alpha projected onto E sub n. B sub n is just a projection of the state beta, or the vector beta, projected onto the nth eigenstate in the basis. So that's vectors. Operators are items that linearly transform one vector into another. So we can write that like this. So if you have a relationship where beta is equal to the operator Q applied to alpha, then its representation of that operator is just a set of matrix elements Q sub mn, where the Q sub mn is just equal to the inner product, or the expectation value, or the inner product of E sub m operator Q E sub n, where m and n vary over all the states in the set. And so these can have diagonal and off-diagonal elements, but it's pairwise. So there's always one on one side, one on the other side, whether they're the same or different. So if we now take beta, which is equal to sum over n up here, B sub n applied to times the ket E sub n, summed over all n, and then we say that that's equal, according to this equation, to Q applied to alpha. Well, we can bring the Q into the sum because it doesn't act on the coefficients, and so you have the sum over n of A sub n Q applied to E sub n. If we now close this inner product with E sub m, then we get, for the first part on the left, we get sum over n, B sub n, E sub m, E sub n. Then you have, on the right, sum over n, A sub n, E sub m, Q, E sub n. Well, this is just Q sub mn. And this only gives you something when n is equal to m. And so this gives you that the coefficient B sub m is equal to the sum over n of the matrix elements of the matrix Q applied to the individual coefficients along the basis set. This is nothing more than vector being transformed by a matrix. So it's just the definition of a matrix applied to a vector. So just as for a vector, an operator's representation will depend on the basis in which it's expressed. For example, if you have a momentum operator in position space, That's the basis of the position operator. We know what that is. We've studied that before. That's just minus I h bar partial with respect to x, and that is the momentum operator. But in momentum space, this just becomes p. Very simple. Similarly, the position operator has different representations in position momentum space. So in position space, it's just x. But in momentum space, this operator becomes IH bar partial with respect to p, in analogy to the one for the momentum in position space. So up to now, we've just described the state of a system by its wave function in position space. This is what we've been working with the entire time. But that's just one representation of the state of the system. It is the representation in the position basis. And that is psi of x and t is simply this inner product of the eigenstate with the eigenvalue, eigenfunctions of eigenvalue x projected, or s of t projected onto each of the values of x, potential value eigenstates of x. So this is convenient and will continue to be used, but you have to remember that it's just one possible representation of the state in the of this system in Hilbert space. We have equivalent representations if we closed it with p, or if we closed it with E sub n, we would get equivalent representations, but in a different basis set.